Okay, I'm going to get started. Last class we talked about the propagation, reflection, and refraction of light by matter. That's basically, we talked about the interaction of light with matter. The understanding of the interaction of light with matter, the propagation, reflection, and refraction of light by matter, is an understanding that's based on understanding that light is electromagnetic, it's electromagnetic fields, and that matter is electromagnetic, it's electrical charges and electrical currents. Out of that understanding comes the laws of propagation of light through matter, law of proper reflection of light in matter, and law of refraction of light in matter. So those laws we met in last class for propagation, reflection, and refraction of light by matter are based on understanding that light is electromagnetic and that matter is electromagnetic. Today's class we're going to use those laws, and next class we'll use those laws. We're going to kind of tame light, and we're going to use light to build light instruments, optical instruments, and we're going to explore this world. This is really kind of the birth of modern biology, because understanding light enabled the building of microscopes. This is kind of the birth of modern astronomy, because understanding light allowed scientists to build the first telescopes. And so the birth of modern biology, the birth of modern astronomy is occurs when we started to understand light. We started to understand the properties of light, the propagation, the reflection, the refraction of light. Okay. Specifically, in today's class, I want to talk about these three topics. I want to say a little bit in general about formation of images by arrangements of lenses and mirrors, just general remarks on that. That's the first bullet. Then I want to talk about specifically images that are formed by plane or flat mirrors, the properties, the characteristics of images formed by flat mirrors, planar mirrors. We'll discuss the equations that describe that, and also how to ray trace, make diagrams of that. And then we'll talk about images formed, third bullet, images formed by curved mirrors. And again there, we'll talk about the properties, the characteristics of the images formed by curved mirrors. We'll look at equations that describe the images formed by curved mirrors, and we'll learn how to ray trace, make drawings, sketches of the images formed by curved mirrors. So this is the plan for today. Here's just a slide to introduce the idea, introduce the concept of an image. So what is an image? What do I mean when I say the word image? What I mean is a copy or a representation or a likeness of some real object. And so here's a couple of examples on this overhead, one on the left and one on the right. On the left is an image formed of an object by reflection in a mirror, and on the right is an example of an image formed of an object by a lens. So on the left-hand side, let's look at the trees here. These trees are images of trees. These are not the real trees. These are the images of the trees. So this is a likeness, a representation, a copy of the real tree. And this is a image that's formed by a mirror. This is a mirrored surface here. This happens to be a convex mirror. I'll discuss that later. And this image has certain characteristics, certain properties that I'm just going to list and we're going to talk a lot about. But one property of the image of the trees is that they're the right way up. So the roots are at the bottom, the leaves are at the top. Another property is that this image of these trees is smaller, it's minified, it's shrunk compared to the original trees. And another property that we'll talk about is that this is actually a virtual image. So virtual means that the light appears to come from somewhere behind this mirrored surface, but it actually can't come from somewhere behind that mirrored surface, because behind that mirrored surface is just a wall or concrete or some material. And so that's what we mean by a virtual image. But we'll discuss this much more as we walk through the examples in today's class. Here's an image formed by a lens. Again, it's a copy, a representation, a likeness of a real eye, but this is the image of the eye. It's an image that's formed by the lens by refraction in the lens, like the image with the mirror was formed by reflection off the mirror. So this is an image with a lens that's formed by refraction, the bending of light rays. And this image also has some properties. So in this particular case, this happens to be a convex lens. We'll see what that means later. This is an image that is also upright. It's the right way up. Look, the eyebrows at the top. This one's magnified. This one was minified. So this one's bigger than the real image. You can do that too. And this is actually also a virtual image. It's also an image where the light appears to come from somewhere, but actually doesn't come from that location. So, keys to understanding the formation of images. What are the keys to understanding these images formed? Well, the keys to understanding them depend on whether we're talking about mirrors, that's today's class, or talking about lenses, that's next Tuesday's class. In the case of mirrors and today's class, the key is the law of reflection that describes the reflection of light of a mirror. So that's the key. That's just the key property that we need for today's class. In next Tuesday's class, when we're talking about images formed by lenses, the key to understand the images formed by lenses is just the law of refraction, the bending of light as it passes through a lens. So the keys to understanding the images from mirrors and lenses are laws of reflection and laws of refraction. They're the basis of our work in today's class, next class. What we'll discover is that there's a whole world of images that you can make. This is where we've kind of tamed light. We've tamed light, we've understood light, and now we can utilize light to make things like magnified images. Sometimes you want to magnify something. We can make minified images. Sometimes you actually want to make something smaller, shrink something. We can make images that are the right way up, and we can make images that are upside down. And we can make images that are the virtual images that I mentioned on the last slide, but also images that are real images, where the virtual images, it just appears the light comes from that location, where the real images, the light truly does come from that location. So there's this whole world of different images that we can make. Magnified, minified, upright, upside down, virtual and real, and we're going to explore that world. And this is the kind of the taming of light for microscopes, telescopes, modern astronomy, modern biology. This is where it all started. We're going to meet some equations for images in today's class. The equations that we're going to meet in today's class are simple equations. They are approximate equations. The full equations for images are actually very complicated because no image is perfect. All images have little aberrations, we call them, little distortions, we call them. If you start dealing with the aberrations or the distortions, it gets very complicated. But if you ignore the aberrations and distortions, we got some simple formulas. That's what we're going to work with. Okay, today's class then is just based on the reflection of light by planar mirrors, flat mirrors, or curved mirrors. What we see are convex and concave mirrors. And the only thing we need to know to understand these images formed by planar or convex or concave mirrors is the law of reflection. So I'm just reminding you of that law we met in the last class, the fact that if light strikes a surface and bounces off the surface, the law of refraction says that the outgoing angle, which we call the reflected angle, theta subscript r, is equal to the incident angle, the incoming angle, which we label theta subscript I. So that's the law of reflection. That's all we need from last class for today's class. Okay, so let's start with flat planar mirrors. That's the simplest place to start. Let's look at the equations for that, how to ray trace the images formed by flat planar mirrors, and then we'll move on to curved mirrors, the convex, the concave mirrors, and the equations, and how to sketch the rays in those cases. Okay, here's I would call this a ray tracing diagram. So I'm tracing light rays in this diagram. And I'm tracing light rays in this diagram that are reflected off a mirror. And I'm using that ray tracing of the light reflected off the mirror to find the image that's formed by an object. So it might be the image of a tree that's formed by the real tree. Might be the image of you that's formed by the real you. So let's take a look at the picture. And let me just explain some of the things that are in this picture. Here's the mirror over here on in the center. And the left side of this mirror is the silvered surface of the mirror. It's the reflective surface in the mirror. This axis here, this horizontal line here, is just an imaginary line. It's just a helpful line. It's called, we give it the name, the optical axis, and it just passes straight through the mirror, perpendicular to the mirror's surface. So it's just a helpful tool for us. On this axis, I put this green arrow. I've called it the object. This is the real object. This is the you that we're going to make an image of. This is the tree that we're going to make an image of. And so this is the object, and we often give it the symbol O for object. Here in magenta, this is the image of that object. This is the location of the image of the object. And I'm just indicating with this magenta arrow here, and we often give that image the symbol I. And so this is the object, the tree or you. This is the image of the tree or you, formed by the mirror. And we're going to see how to construct this image location from that object location. So that's the key thing that we want ray tracing for. On the picture, I've sketched a couple of light rays that reflect off the mirror. These light rays emerge from the object, the you or the tree. They reflect off the mirror. They're seen by whoever this is, the giant eye over here. And that eye interprets where the image is located. So let's trace these rays. One of them is in blue, upstairs here, and another one, a second ray I traced, is in red here. And let's see how, by tracing these rays from the object, reflecting off the mirror, into the eye, we can reconstruct where the eye and the brain behind the eye thinks the image is. So let's start with the blue ray. Blue ray heads parallel to the optical axis, which means perpendicular to the mirror, strikes the mirror and reflects off the mirror. Now this blue ray, because parallel to the optical axis, is striking the mirror at an incident angle at 0 degrees, which means it reflects at an angle of 0 degrees. So it heads back along the path it came along because it's striking the mirror perpendicular to the mirror. That's the law of reflection. And so here goes the outgoing blue ray after reflection, heading into my eye. Red ray. What's the red ray doing? The red ray, I've drawn a red ray that's convenient. It heads from the top of the object here, top of the tree, the top of you, down towards the mirror. It's going to strike the mirror at the point where the optical axis passes through the mirror, say the center of the mirror. So it's going to reflect off the mirror and head back towards the giant eye over here. And again, it's going to obey the law of reflection. So the incident angle, the angle above the optical axis, must be equal to the reflected angle, the angle below the optical axis. And so that's the law of reflection, and that's what I drew. And so here goes the red ray. Now over here, the eye. The eye collects that light, these two light rays. There's many light rays, but it's going to collect at least these two light rays. And then the brain interprets where that light is coming from. Now they both started out at the top of the tree, or top of you. And so the eye and the brain are going to reconstruct where's the common point that they come from. So it traces the blue ray back in the direction it was coming from. That's this dashed line here. Traces the red ray back in the direction it was coming from. They come from this common point here. This is the location of the image. So this is where the eye and the brain and the person reconstruct the image to be, at this location here. And so we've been able to ray trace rays from the object, bouncing off the mirror into the eye, and find out, based on where the object position is, where the image position is going to be located. So that's ray tracing of the image formed by an object in a plane mirror. And it just comes down to that. And all we used was the law of reflection. Based on that ray tracing and a little bit of geometry, and the geometry is just geometry of triangles and similar triangles. But based on a little bit of geometry and similar triangles, you can construct two equations that at their core, at their heart, are based on the law of reflection, which itself was based on electromagnetic theory and understanding the electrical nature of matter and light. The two equations are these two equations which describe the nature of the image that's formed of the object. This equation over here on the left. This equation tells you where the image is located for a given location of the object. The P in this equation is the location of the object. It's the distance of the object from the mirror. And so here's P, and in green here was the object, and so this is the object distance. Q here is the image location. So it describes the image location. And here is the image location in magenta here, and this Q describes the distance from the mirror along the optical axis, or where the image is located. So Q equals minus P. Q has the same size as P for a planar mirror, so it's the same distance from the mirror as the object. The image is the same distance from the mirror as the object. But you notice that Q will have the opposite sign, because Q equals minus P. So what does that sign mean? If we put the object in front of the mirror, which we'll always do, we call that a positive distance. The image is actually formed behind the mirror, and that's the negative direction. So that's a negative distance. And so the fact that the image is behind the mirror, where it physically couldn't be, right? Whereas the object is in front of the mirror, where it physically was, is denoted by the fact that Q will be a negative number here, indicating behind the mirror, but P will be a positive number, indicating that it's in front of the mirror. And so that tells us everything about the image position, right? Whether it's in front or behind the mirror, and also how far in front or behind the mirror it is, given the location of the object. Second equation. This equation over here tells us a couple of things. It's going to tell us whether the image is bigger or smaller than the object, so whether it's magnified or minified. It's going to tell us whether the image is upright or inverted. It tells us both those things. For the case of the planar mirror, the height of the image is actually just exactly the same as the height of the object. So it's neither magnified nor minified. It's not shrunk or enlarged. It's exactly the same size. That's a characteristic of a planar mirror. The fact that I put the plus sign in here means that the sign tells you whether that image is upright and inverted. If it's upright, the same way up, if the tree's leaves are at the top and the roots are at the bottom, then that would be an upright image, and that would be a positive value of H here. If the image was inverted, it's not the case here, then we'd have a negative value for the this height of the image. Typically, we think about, rather than this equation here, we think about what is the magnification. What is the magnification of the mirror, of this object, of this image of this object in the mirror? The magnification is just the ratio of the height h prime of the image position to the height h of the object position. In this case, it's just +1. So if we just divide through by h, then h prime over h is just +1. That's the magnification of a planar mirror. So the size, 1, means the image is exactly the same size. It's not enlarged or shrunk. And the +1 means that it's the right way up. It's not inverted. It's not upside down. Okay. I can just show you quickly. I think I'll do this on a video. The rays that we constructed. To form the image from the object, and from which the equations of image formation in a planar or a flat mirror are derived or obtained. So in this arrangement here, I've actually got it on the board here, but it's fallen off. I've got an arrangement here that produces 3 beams of light. So this central line here, you'll see a laser beam emerge from that. Upstairs here, above that horizontal line, there'll be another parallel laser beam, and below it there'll be a third parallel laser beam. So I'm going to shine 3 parallel laser beams, and in this arrangement here, I can mount a mirror. And I'm going to mount, first of all, I'm just going to mount a flat planar mirror, which is the mirror that we've been describing. And so let's go ahead and do that. Here I am. This is a flat planar mirror, and I'm just going to bolt it into this arrangement here. And now I'm going to go and turn the lights out, if I remember this. Yeah, turn the lights out, and then I'm finding my way back, and I turn on the arrangement, and I'm shining these laser beams at this mirror here. Now because these laser beams are striking the mirror normal to the surface of the mirror, they're reflected back in the original direction. But now look, I'm twisting the mirror, and you see different rays that are striking the mirror not normal to the mirror, and they're reflected in a way that's obeying the law of reflection. And our whole calculation, computation and sketching of the image of an object in a planar mirror was based on that law of reflection. Okay. Let's move on then. That's planar mirrors. Let's move on to curved mirrors, where we'll see there's actually 2 types of curved mirrors that we call convex and concave. Every curved mirror has a little personality. It's a simple kind of personality. There's not, I don't know, there's 4 main human personality traits or whatever they are. I seem to remember this thing called ocean. It was the way of remembering them. But a mirror, getting off track, a mirror just has one personality dimension, and it's its focal length or its focal point. So mirrors, curved mirrors, are described by a quantity that's called their focal length or their focal point. And that's what this overhead is meant to introduce, is meant to describe. So in this sketch here, this is basically a sketch of a curved mirror. And as I mentioned, the mirrored surface, so on the left here is the mirrored surface. That's what the light would reflect off. The mirrored surface can kind of be curved inwards, which is what I drew, or it could become curved outwards, which is what I didn't draw. So that's the two types of mirrors. A kind of concave surface, or what we call, if it's curved the other way, a convex surface. So this is a concave mirror that we'll see converges light rays. The other type is the convex mirror that diverges light rays. Anyway, here's a concave mirror, here's the optical axis, and on the optical axis, as it passes through the center of the mirror, I marked two important points. One of the important points is the radius of the curvature of the mirror. See, that would distinguish one concave mirror from another concave mirror. One might be concaved with a small radius, and one might be gradually concaved with a large radius. So that would be a difference in their personalities. And so the radius of curvature that we call uppercase R is kind of the characteristic of the concave mirror. This other point, which is more useful when ray tracing, is called the focal point. This distance from the lens from the mirror is called the focal length. And this point, F, the focal point, is actually just half the radius of curvature. So it's halfway between the mirror surface and the radius of curvature. That's the focal point. And I wrote that down here. For a concave mirror, the case I drew, that point is going to be on the mirrored side of the mirror, the side on which the light will exist. And we call that focal point, we call that focal length a positive focal length, when the focal point is on the mirrored side. When we come to meet a convex mirror, which is curved the opposite way, that convex mirror actually diverges light, and its focal length or focal point is on the back side of the mirror, and we give it at a negative sign to indicate it's on the other side, the back side. And so we'll meet those details as we look at some examples and illustrations. Okay. So that's the personality of a lens, basically, of a mirror. Here's ray tracing for a concave mirror. Okay, so in this is a kind of busy slide, but in this busy slide, I'm doing the same thing as I did for the planar mirror, the flat mirror. I constructed the image formed by an object by ray tracing. In this slide, with this concave mirror, I'm going to construct the image formed of an object by reflection of the concave mirror and using the law of reflection again. So I'm doing exactly the same thing. So let's take a look at this ray tracing that I've done over here. We're going to focus on this bit of this slide. Here's the mirror. The left-hand side is the front of the mirror. That's the mirrored side. The right-hand side is the back of the mirror. That's, where the wall is or whatever. Horizontal line is the optical axis again. On the optical axis for the curved mirror, I've marked these important points, which is the radius of curvature and the focal length, or the focal point. So those are labeled here. And I've indicated my my object over here. Remember, with the way we sketch our images and objects are vertical arrows on these ray tracing diagrams. And so here's my object. So this might be you, or it might be the tree, or it might be the whatever that we're making the image of. And then over here has appeared the image. This arrow here is the location and the properties of the image that's formed of this object when light is reflected off the mirror. So we're going to construct this image position from this object position by light rays that emerge from the object, just like they did with the planar mirror, that they reflect off the mirror, just like they did with the planar mirror, and then they head back towards the left, and they're going to enter our, I didn't draw the giant eye here, but enter a giant eye over here and be interpreted by my giant brain. And so that's what's going to happen. Okay, so let's see how we figure out this location of the image and its properties based on this location of the object and reflection off this mirror. Look, the image is not the same distance from the mirror as the object was. It's different in this case. The image is not the same size in this case, and the image is actually the upside down in this case. So suddenly, by having a curved mirror, we've really changed the properties of the image. For the planar flat mirror, it was the same size, the same distance, and it was upright. That was all very simple. For the curved mirrors, we're going to see that we can make minified, magnified images. We can make them in front of and behind the mirror, and we can make them upright and inverted. We're going to see all that world. Let's look at the rays I'm drawing. I've drawn 4 rays here. You don't need to draw 4 rays, but I wanted to show you all 4 rays that typically can be drawn, and you can pick your favorites typically. But anyway, let's take a look at these rays. I'm going to start with what I call the simplest physics ray. What's the simplest physics ray that heads from the object, bounces off the mirror, and heads back towards the eye? I think it's this black ray here. It's the one that strikes the very center of the mirror where the optical axis is and reflects back off. So we're thinking about this ray from the hat of the person over here, striking the mirror and bouncing off. It's got to obey the law of reflection. So in this case, it's very easy to draw that the angle that it strikes the mirror above the optical axis is equal to the angle that emerges from the mirror below the optical axis. That's just the law of reflection, that theta I equals theta R. And so this is one ray that we can draw. A second ray, let's take a look. What is the second ray? I said the geometrically simplest. Another ray that's really simple is if this ray from the top of the object heads towards the mirror and heads through the radius of curvature, so that's this special point C here, it's going to strike the mirror, and because it's going through the radius of curvature, it's going to actually strike the mirror at 0 degrees incident angle, which means it gets reflected at 0 degrees incident angle, which means it gets reflected along the path it came from. And so this light ray is just going to head back in the direction it came from. Again, that's the law of reflection. So that's a simple ray that you can draw. The one that goes through the radius of curvature comes back along the same direction that it headed towards the mirror. And so here's this red arrow going out towards your eye. The other 2 rays, the blue and the green, I said they're cousins, or they're like brother and sister, or whatever. They're cousins of brother and sister because one of them heads in parallel to the optical axis and then heads out through the focal point. The other one heads in through the focal point and heads out parallel to the optical axis. Now, why is that the right ray to draw? Why does a ray parallel head out through the focal point, or a ray through the focal point head out parallel? The reason for that is those combinations obey the law of reflection. So these also are rays that the incident angle and the reflected angle are the same. And that leads to the fact that parallel in, you get out through the focal point, and through the focal point in, you get out through the out parallel to the optical axis. So the green one goes in through the focal point and then comes out parallel to the optical axis, and the blue one goes parallel to the optical axis and out through the focal point. But this green line over here is heading out this way. This blue line is heading out this way. We need a really giant eye to see the blue line. But all of these rays are collected by our eye, and our eye passes those rays to our brain, and our brain goes off thinking, where do they all come from? You know, they came from the top of the tree, or the hat on your head. They came from a common point on the object. So where do we reconstruct that common point to be? Well, let's trace all these rays back. I'm going to trace the black ray back, the red ray black, the blue ray, and the green ray black towards the mirror. This is the common point they come from, and this is where the image is formed. So we reconstructed the image location with this ray tracing. Notice that in this case, one thing about a concave mirror, which is this example, every ray gets bent towards the optical axis. So that's a check that you're drawing the rays correctly. You better check that if you've got concave mirror, everyone's got to be bent towards the optical axis. We'll see with convex mirror, that's diverging. Every ray gets bent away from the optical axis. So this green ray got bent towards the optical axis. This red ray gets bent back towards the optical axis. It literally crosses it. This blue ray got bent towards the optical axis. It literally crossed it also. So that's ray tracing. Based on that ray tracing, again, and sort of high school similar triangle geometries that we all love, you can construct two equations. One that kind of parallels to the planar flat mirror equation. One described the location of the image, and the other one described the magnification of the image and whether it is upright or inverted. That's what these two equations describe. So what we call the mirror equation describes the relationship between the location of the image, which we were figuring out, so that's Q, remember, and the location of the object, that's where we put the object, and the focal length of the mirror. This curved mirror has a focal length. And so that's the mirror equation. So remember that P was the distance of this object from the center of the mirror along the optical axis. So my laser pointer is telling you what P is. Q is this distance of the image from the center of the optical axis. So here's Q. And the focal length was, well, here's the focal point. It's this distance here of the focal point from the center of the mirror. So this is the relationship between the two. If you know what your mirror is, you know the focal point, and then you place your object at a certain position, then you can calculate with this equation the image location. So that's how you would calculate it. Again, there's sign conventions here. Our focal length for a concave mirror is positive. Locations in front of the mirror are also positive. So in this case, both P and Q are going to be positive. If the image was formed behind the mirror, that would be a negative image location. Let's just demonstrate the capabilities of this mirror. This concave mirror is very, very interesting, I think. Of mirrors, it's my favorite. It's my favorite because it can both magnify and minify. So it can make things smaller and bigger. It can make things upright, the right way up, or inverted, upside down. And it can make both the real and the virtual images that we talked about. The images where light does or doesn't actually come from the apparent location of the image. So let's take a look at a demo of this. So in this video, I've got a large concave mirror. Here it is. And this is a concave mirror. So it's like a cave, forming this little cave. And here it is over here. And I'm going to walk towards the mirror with a camera, and you're going to see the image of me in the mirror as I carry that camera. This is very hard to see right now, but this is me. Because when I'm standing over here, this is the image of me that is being recorded by the camera. So I'm standing there. And let's play this. And as I'm going to walk towards the mirror, so I'm going to change. What am I doing here? I don't know. What I was doing there was I was at a certain location, image distance, looking at where my object, I was at a certain location, object distance, and I was looking at my image, right? My image is behind, it looks like it's behind the mirror. And then I'm going to change my object position. I'm going to walk towards the mirror, and I'm going to look at how the image position changes, what happens to it. So I'm exploring the nature, the properties, the characteristics of the concave mirror and its image formation of an object. Okay. It sort of seems like I've had a couple of drinks when I'm doing this, kind of wandering around a bit. But look, here I come. I'm inverted, by the way. I get close to the mirror and I'm the right way up. That actually happens for a concave mirror when you walk through the focal point. If you're inside the focal point, you're magnified and the right way up. If you're outside the focal point, you're inverted and minified. So that's a very interesting feature of this mirror. I'll do that one more time, just so we can see it again. You're seeing the world of images formed by a concave mirror. Again, I'm far away, object is far away, image is inverted and minified. I'm getting closer and closer and closer, and then there's going to be a bam, and I've walked through the focal point like a sort of mysterious portal, and now I'm the right way up, and I'm magnified. And then I'm going to walk back out. Again, I go through the focal point, and I become inverted and minified. Okay. I have no idea what I'm doing now. The other type of mirror is a what did we just do? I've forgotten. Concave mirror. Now I'm going to do convex mirror. So concave mirror is kind of, the mirrored part is curved inwards, like a little cave. That's the way I remember. Convex mirror is the other way around. I'm stretching, I'm doing yoga. And that's a convex mirror. The concave one, the one that's curved in, that converges the light towards the optical axis. The convex one is the one that diverges the light from the optical axis. So we had two slides for the concave mirror. One was ray tracing for the concave mirror. We were learning how to do that, exploring how to do that. And the other one was the equations for Q and its magnification. The image properties for the concave mirror. Got the same thing for the convex mirror. I got a ray tracing slide, and then I got the equation slide. So it's exactly the same pair of slides. The only thing that's changing is now, if we look at this diagram here, this mirror is a convex mirror rather than a concave mirror. So again, on the left is the silvered side of the mirror. That's the reflective side of the mirror. This is on the left, the front of the mirror, where the light is going to be. This is the back of the mirror, where the concrete wall or whatever is. Okay, so here's the mirror. Here again is our old friend, the optical axis that goes through the center of the mirror. And again, we're going to mark on the optical axis the object position and the image position. So I've marked the object position as this vertical arrow here in gray. I've labeled it O for object. I've marked the image position in whatever this color is here, pink or something. And I've labeled that with an I for image. So those are the object and images positions. The object, I've just placed the object there, and I'm going to explore where the image is located. The image is located apparently behind the mirror, so it's a virtual image because the light really can't come from there. Also, it's smaller than the object position, so somehow the image has appeared smaller. It's been minified, but it is the right way up. It's the same way up. The hat on the person over here is at the top. The hat on the image of the person is at the top. How did we locate that image? You know, I put the object at a certain position, but then I've just drawn where the image is and said that's where the image is. How did I figure that out? I did some ray tracing again. And again, there's 4 rays that I could conveniently draw, and I'm just going to walk through those 4 rays and construct the location of the image based on the location of the object. Okay, so I'm going to draw my rays from the top of the object so I can reconstruct the top of the image. I said that my favorite physics ray, which I'm going to draw in black, is this ray that strikes the mirror and reflects back towards the giant eye and the giant brain that are interpreting the results over here on the left, strikes the mirror at the very center of the mirror where the optical axis passes through the mirror. That ray obeys, like all rays, the law of reflection, where the angle of incidence, that's the angle of this ray above the axis, is equal to the angle of reflection, which is the angle of ray below the axis, and that's easy to draw. For this simplest physics ray, I've just drawn an angle theta I above the optical axis and a matching angle theta R below the optical axis, and so here's this reflected ray in black, and it's heading off towards this giant eye. What was the second ray I drew? I think I drew the ray that I claimed was the geometrically simplest ray. It's the ray that heads towards the focal point. Now, here's a key point. This is a very important point. For the concave mirror, the focal point was positive and in front of the mirror. It was on the silver side where the light is. For the convex mirror, the focal point, the focal length is negative. It's on the back side of the mirror where the light can't exist. So look, here's a big difference. This focal point that I've drawn for the concave mirror is on the back side. The focal point that I drew for the convex mirror was on the front side. That's distinguishing a convex and a concave mirror. Right there, plus or minus focal lengths, positive and negative focal lengths, whether the focal point is on the side with the light or the side behind the mirror. Anyway, here's my focal point. So, and here's my radius of curvature. The radius of curvature of the mirror is about this point. So this is also on the back. This geometrically simplest ray, the red ray, heads in towards the radius of curvature, which is now on the back of the mirror. It's going to strike the mirror and head back along the path that it arrived from. So that's this red ray here, and this is that reflected ray heading in towards our eye. This is simplest because it strikes the mirror with an incident angle of 0 degrees. It's reflected from the mirror, a reflected angle of 0 degrees, so it's heading back along the path it arrived in. Okay, so that's the red ray. And then remember the cousins, or the brother and sister? Remember, because of the law of reflection, there are two rays, one heading in parallel that heads out from the focal point, and one heading in towards the focal point that heads out parallel. They obey the law of reflection, and those are the other rays that you can draw. So let's just look at those. One heads in parallel, this blue ray here, and in the convex case, we drew the reflected ray as coming out through the focal point. In the concave case, we draw the reflected ray as coming out in a direction as if it came from the focal point, because that's behind the mirror now. And so here's the reflected ray in this case. This is obeying the law of reflection, and this ray is heading out into what now needs to be a really, really giant eye. The green ray, that's the one that's heading in towards the focal point. In the convex case, concave case, we actually pass through the focal point. But now the focal point's behind the mirror, we can only just head towards the focal point. Once it strikes the mirror, heads out parallel to the optical axis. And so that's brother and sister, or cousins there. All these rays are collected by the giant eye on the left, interpreted by the giant brain on the left, and the brain says, where do they all appear to come from? That's where the image is going to be located. It traces them all back, and you see this is the location, this point here. The top of the image arrow is the point that all these rays appear to come from. They all appear to come from this point. And so that's where we reconstruct the image. And so that's where I drew the image. That's how I found the location of the image, by this ray tracing, using the law of reflection. Okay. So that's an image that's also interesting because completely unlike the flat planar mirror, where the image was same side behind the mirrors, the object was in front of the mirror, and it was the same size, and it was upright. This image is less distance behind the mirror than the object was in front of the mirror. It's also been shrunk, it's minified, its magnification is less than 1, and it is the right way up. It's also a virtual image because the light actually can't come from there. No light can come through the wall and through the back of the mirror. It just appears that the light comes through there, and that's what we mean by a virtual image. This is the equation that describes the properties of the image and the performance of the convex mirror. It relates the location of the image, which is what we call Q, to the location of the object, which we call P, and the property of the particular convex mirror, which is determined by its negative focal length F. And it also tells us the magnification of the image, both whether the image is bigger or smaller, that's the size of the magnification, and whether it's upright or inverted, that's the sign of the magnification. So it tells us all of those things. You'll notice, this is handy, these two equations are the same as the two equations for the convex mirror. So convex, concave mirror, concave mirror. Convex and concave mirrors, the mirror equation saying the location of the image, and the magnification equation saying the size and the uprightness of the image, they're the same equations. They just work differently because in one case, concave, focal length is positive. In the other case, convex, the focal length is negative. So that makes all the difference when you start plugging in the numbers. But the equations, conveniently, handily, are actually the same. Let me just show you a quick demonstration of this. Going back to this video, but hey presto, I'm going to change this from a concave mirror to a convex mirror. But I'm then going to do the same thing. I'm going to walk towards it, videoing myself, videoing my image, and then walk back away from it. And we'll just get to see the world of a convex mirror. Okay, so now I swapped it over. And you can see the different shape, the different curvature of the mirror. Now I'm walking towards it. Look, I'm always upright. I just stay upright. I'm smaller than I really am, but I stayed upright all the way. And then I walk back. I also appear to be behind the mirror, don't I? But I mean, the image can't really be behind the mirror. It can just appear that way. And maybe we can do that one more time. Okay, so here's again this convex mirror. I'm upright, I'm behind the mirror, I'm shrunk, and then I get as close as I can, and then I'm going to walk backwards, and all the time I'm still upright, I'm shrunk, and I'm virtual. I'm behind the mirror. Story of my life. Okay. So concave mirror, a little less flexible, I would say. Concave is a little more flexible than convex mirror. Concave could magnify and minify, for example. Convex can only minify. Convex mirrors are the things that you see in a supermarket or a convenience store or whatever, so you can watch the whole store from the cash till because it shrinks everything, which means you see more. So it's just because it doesn't magnify, just because it minifies, doesn't mean it's a waste of a time mirror. It's actually a very useful mirror if you own a shop. It's also used on, like, the wing mirrors on your car, side mirrors on your car. They can be convex, so you can see more. You can shrink stuff and see more behind you. I mean, one of the big reasons we use mirrors is to see behind us. Don't know what I'm doing anymore. I just wanted to say that as we introduce mirrors and lenses, we're going to have a lot of conventions about what a plus sign and what a minus sign means. You know, whether you're in front of a mirror or a lens, whether you're behind a mirror or a lens, whether you're positive or negative focal length and what that means. These are hard things to just keep in your head. You'll get an equation sheet, or you get a table on the exam that summarizes all these sign conventions, like positive P is in front of the mirror, a negative Q is behind the mirror, a concave mirror has a positive focal length, a convex mirror has a negative focal length. You won't have to remember all that, I'm just saying that. Let's move on. With an example. So I've got two examples in here. I really hope I get to both of these, but let's try. First one was with a planar mirror, and then the second one was with a convex concave mirror. In a sense, the planar mirror question I've got here is a little bit more steps and complicated than actually the concave convex mirror, which is more just utilizing equations and ray tracing. In this question here, we've got a choir and we've got an organist. So this picture here is like I'm in a helicopter looking down on the choir and the organist in a room. Here's the choir lined up against the right-hand wall. Here's the organist close to the left-hand wall. And here are the dimensions of the room and the location of the organist. And we're told that the organist is looking at the choir in a mirror. And the question is, you know, how much of the choir on the right-hand mirror can the organist see? Can the organist see all the choir? Well, think about when do we use mirrors to look behind us? Most often we use it in the car, right? We use the rear view mirror, or we use the side mirrors. You don't see, when you look in one of those mirrors, because of the size of the mirror, you don't see everything behind you. And so here what we're going to do is calculate how much, what range of the rear wall, the right-hand wall, we see behind us, or the organist sees behind them in the mirror. To solve this problem of how much of the wall the organist sees, by looking in this mirror here at the right-hand wall over here, this is a story, or this is kind of a tour of what we've done today. It's a tour of image properties in planar mirrors. It's a tour of ray tracing, this case for planar mirrors. It's a tour of the law of reflection, which we've used constantly during today's class, and also you'll be very pleased to know it's a tour of high school geometry that we all love and remember that class. Okay. Some of us think, oh, I never took that class. I understand that also. Okay, so I got a bunch of slides, but they're really sort of cartoon slides that I can go through quickly. This first slide, the first thing in working with this problem and finding how much of the rear wall that the organist can see, how much of the choir the organist can see, is to understand the image that's formed of the rear wall, that's the object, in the mirror, and that's viewed by the organist. And that just involves using the properties of an image in a planar mirror. And we said that the image of an object in a planar mirror is the same distance behind the mirror as the object was in front of the mirror, and it's the same size. It's not magnified or minified, its magnification is 1. And so that's all I'm drawing here. Here's the choir against the right-hand wall. Here's the mirror that the organist is going to look in. Here's the image of the object. This is the image of the choir in the mirror. And you see that I've just drawn its properties. I've made it the same size. The image is the same size as the object. And I've made it the same distance behind the mirror that the object was in front of the mirror. So Q and P are both, these are just the distances, the magnitudes. They're both this 5 meters. Okay, so that's a quick reminder of images properties in planar mirrors. Now, to solve this problem, we're going to do some ray tracing. And so I'm going to show you a few rays, and I just thought I'd show you one ray and then add a few more rays and then talk about a very important ray over the next few slides. What are the rays that are relevant to the organist seeing the choir in the mirror? Well, here's one example ray. This is a light ray that comes from this particular choir boy, strikes the mirror, reflects off the mirror, obeying the law of reflection, and goes into the organist's eye. And the organist sees that light ray and says, well, that's coming from this image that's located over here. So that's a typical ray that is seen by the organist of the choir based on reflection of the mirror. The organist looking at the image of the object in the mirror. We could draw a whole bunch of these rays, right? And I literally did that. I got quite carried away. Here is a whole bunch of them. Here's the ray that came from the top choir boy that formed an image over here. His colleague next to him, right? There was a ray bouncing off the mirror here. The image of that choir boy or choir girl is over here, and so on and so forth, right? Each of these rays forms an image over here based on reflection. You'll notice on this picture, right, as we walk, say, from the center of the choir to the edge of the choir, the rays that come from the center of the choir to the edge of the choir, the rays that come from the center and form the image of the center, reflect off the mirror very close to the center, whereas the rays that come from the edge over here reflect off the mirror much farther from the center. So the locations of the reflections are quite different for the different choir boys or choir girls over here. Now, one thing about this sketch that I didn't draw quite right is that I drew this big mirror. In the question, the mirror wasn't a big mirror stretching across the whole wall. The mirror was actually a rather small mirror centered at the center of the wall. So let me correct that. Here is the mirror. This is the real mirror in the real problem that has a width that was 0.6 meters. It has a distance that extends 0.3 meters to upstairs here and downstairs here in this helicopter view from the optical axis, from the center of the room here. Now that's interesting because when I made that correction of the imagined big mirror to the real mirror, you realize, like with a rear view mirror in a car or a side window wing mirror in a car, that there are rays, there are regions that you won't see. This ray from the very top choir boy that we drew, right, actually doesn't strike the mirror. So it can't be reflected. We don't see this ray that I've now marked in red and crossed out. The other rays do strike the mirror. But one ray that's especially interesting is this ray that strikes the mirror right at the edge of the mirror, because that's the ray that kind of defines, it's going to define how much of the choir you see. If you're within the range of this wall, I called it a wall-defining ray because I couldn't think of a better word. But if a choir boy is located, or girl, is located within this range, this ray here, then you're going to see that choir boy or choir girl. But if they're outside that range, you won't see them. And so this is a very important ray that strikes the edge of the mirror, and that's the one I'm going to focus on to solve the problem. So here is just that ray, and I've just annotated that particular ray with all of the dimensions that we were given in the original problem, and with the law of reflection. So this ray is traveling towards the mirror, and it's striking this corner of the mirror, right, which is 0.3 meters above the optical axis. When it strikes the mirror, the incident angle that it strikes the mirror determines the reflected angle that it emerges from the mirror. And so this is the reflected ray. And so here I'm just concentrating on this ray, and I'm also concentrating on the fact that I know the distance from the optical axis where this ray strikes the mirror, and I also know this distance here, the organist distance from the center of the mirror along the optical axis. So I know these distances here. So this is where what have I done so far? I first of all showed you a slide that talked about the properties of the image, that it was the same size as the object, and it was the same distance behind the mirror as it was the object was in front of the mirror. So that was image properties. Then I had some fun drawing these ray tracing things, and by drawing all the rays that are reflected off the mirror, I found a special ray, the wall defining mirror, that hit right on the edge of the mirror. I said I'm going to concentrate on that. Then I moved on to drawing that ray in detail and showing you the law of reflection applied to that ray. By applying the law of reflection and drawing that ray in detail, I realized something, that hidden within this ray and the image and the object that produces that ray, the image that's formed by that ray, is actually a little bit of geometry. There's two similar triangles. Let me show you those two similar triangles. There's a little triangle downstairs here. I indicated it in green. And then there's a big triangle here. And I've indicated that in magenta. And these are similar triangles. What do we mean by, can we remember? Can we remember what we mean by similar triangles? Yes. Similar triangles are triangles that have the same angles in the corner. They have the same ratios of the sides. So if you divide one side, the hypotenuse, by the adjacent, you get the same ratio for two similar triangles. They're just different in overall size. One's maybe bigger overall, one's maybe smaller overall. That's exactly the case here. These two triangles, the green one and the magenta one, have the same shapes, they have the same angles in the corners, they have the same ratios of the sides. This magenta one is just an enlarged version of this green one. And that's what I spotted. I want to know how much of the wall I can see. So I want to know this distance, this vertical distance I call y. I want to know that distance. That's the vertical side of the big triangle. Now I know the horizontal side of the big triangle. That's this distance here is 0.8 meters plus is 0.53 meters. And I also know the vertical side and the horizontal side of the little triangle. So now let's just forget all about the optics and stuff like that. Let's just think about triangles. Think about triangles. We've got a big triangle, we've got a little triangle. A little triangle, I know how high it is and how wide it is. Big triangle, I know how wide it is, but not how high it is. But I know there's similar triangles. I know the ratio of the height to the width of the little triangle must match the ratio of the height to the width of the big triangle. I know those two ratios are the same. If I set them to be the same, the only thing I don't know when I set them to be the same is the height of the big triangle, and so I can figure it out. And so this last bit of geometry is how I'm going to solve this problem. What is this distance here, y? And that double that distance is how much of the wall you see. So I actually did that on the next slide. I equated the ratio of the vertical side of the big triangle divided by the horizontal side of the big triangle to the vertical side of the little triangle, the green triangle, to the horizontal side of the green triangle. I just equated those because those are similar triangles. That's true. They have the same ratio. In the case of the green triangle, so I labeled the numbers green, the height is 0.3 meters, the width is 0.8 meters. So it's 0.3, it's 0.3, should be 0.3 meters over 0.8 meters. What about the same thing, so it's height to width of small triangle. What about height to width of the big triangle? Well, I know the width of the big triangle is 5.3 meters plus is 0.8 meters. That's the distance from here to the corner here. So that is, what is that? That's 6.1 meters. So I know that number, but I don't know the height of the magenta triangle. So that I just gave that the symbol y. This is the thing I'm trying to find out. So from similar triangles, equating these similar triangles, the ratio of sides of these similar triangles, I've figured out that an equation for this height, this unknown height, in terms of these other numbers. So I solved it. I rearranged this, found that this distance y is 2.3 meters, which meant that if I double that, the amount of wall that I see is 4.6 meters. And so I solved the problem there. How much of the wall, how much of the choir boys I can actually see. And you could do the same thing for a car mirror, or a rear view mirror, or a side mirror in a car. You could figure out how much of behind you can see. And that's very important, of course, when you're driving. I got 5 minutes. I'm going to try and do this question. I would normally do this one on a document camera, but I'm clearly running out of time. But I at least want to show you the solution to it. This is the curved mirror example that I had. A dentist used a curved mirror. I don't like the dentist, but a dentist used a curved mirror to magnify a tooth. So here we are, magnifying a tooth. The tooth is 1.25 centimeters in front of the mirror, and the image is 10.5 centimeters behind the mirror. We've got to determine the focal length of the mirror and the magnification. Look, what are we being told in this problem? What we're being told in this problem is the image position. It's 1.25 centimeters. It's positive 1.25 centimeters in front of the mirror. We're being told the object, that was the object position, positive 1.25 centimeters in front of the mirror. We're also told the image position. It's 10.5 centimeters behind the mirror. So it's actually Q equals minus 10.5 because behind the mirror is negative. So this is a problem where we're told the image and the object positions, both their sizes and their signs, and we're going to figure out I'll skip that, but you might want to look at it. We want to find the focal length of the mirror and the magnification. Well, this is just an example of those equations that were based on the law of reflection that relate image position, object position, and focal length, that relate image position, object position, and the magnification. I'm just simply using those mirror and magnification equations to solve this problem. Here's the mirror equation, that the inverse of the focal length is sum of the inverses of the object and the image positions, P and Q. I know the object and the image position, so I can just plug them in. Notice I'm not just plugging in the numbers that were given in the problem, 1.25 centimeters and 10.5 centimeters. I was aware, was cognizant of the signs that these numbers must have. Object in front of the mirror, so it's positive position. Image behind the mirror, so it's going to be a negative image distance. So I've got a plus sign here and a minus sign for the front and back side of the mirror. I calculate if I calculate the sum of the inverses of these two quantities, I get the inverse of the focal length. And if I take the inverse of that, I get the focal length to be 1.4 centimeters. So you notice that the object was placed inside the focal length. That's how you magnify with a concave mirror. You saw the magnification of me, right? I only was magnified in the concave mirror when I got inside the focal length. You're seeing exactly the same thing here. So this is what we demonstrated. What about the magnification? Well, the magnification is simply the ratio of the image and object distances. So I was directly told the image and object distances. I've just got to divide one by the other to get the magnification. Again, I'm going to have a negative, that's important, 10.5 centimeters, negative because it's behind the mirror, over a positive 1.25 centimeters, that's the object position, that was in front of the mirror. I'm going to get a number that is 8.4. I magnified the tooth, that's the whole purpose of that mirror. And also I found that that it was an upright image. The picture showed me it was an upright image. It's a positive magnification. So the plus sign means upright. I also got in here a ray tracing of that. Here is the concave mirror. Here's the tooth, the object in front of it. I drew those rays that we talked about, the simplest physics ray, the simplest geometrical ray, and the cousins. I drew all those rays. I didn't color them, though. I reconstructed where they appeared to come from, and they appeared to come from behind the mirror and this enlarged image. And so this is a picture of the formation of image, just like the calculation was a calculation of the image. It's often handy to